Okay, now we can get started for real. Hello everyone. Today I'm going to be talking about sparse autoencoders. This is a very interesting concept within the domain of mechanistic interpretability. Mechanistic interpretability itself is a subset of interpretability, and specifically this is the interpretability of language models, right? So we have a huge 9 billion parameter, even more billion parameter language models where they are doing all sorts of weird things and we don't inherently understand what's happening under the hood. So the idea behind interpretability in general is to give us some way to define exactly what is happening within these language models, and sparse autoencoders is one such technique within mechanistic interpretability. So the general outline for what we're going to talk about, I will cover what mechinterp and interp is. It will be more of a quick review rather than like an in-depth thing, but we'll spend more time on sparse autoencoders, what they are, and then how we can actually train and use sparse autoencoders for a couple of interesting things within mechinterp. Cool. Background and intuition. My favorite way to introduce interpretability is through this slide. I think I've spoken about interpretability a bunch of times and introduced this one in every single presentation, regardless of whether this is like MLI Purdue or not, right? We have a comic. This is XKCD 1838. There is a person standing on a fly left linear algebra and a person to the left that is going, "This is your machine learning system." And the person on the right goes, "Yep, you pour your data into this big funnel, collect your answers on the other side. And if the answers look wrong, you keep stirring the pot until the answers start to look right. And once you get answers that look right, you say, hey, we are done here. This is a trained neural network that works really well, and you should deploy this in production." In practice, this is a very bad idea because you are training on a subset of the real world sample space, right? Or what you're going to see in the real world. And the direct consequence of that is if you learn your data set, you are going to get to a point where you see answers that look correct all the time, but inherently you have not learned anything, you have memorized everything, right? And having that understanding of what is learning and what is memorization is very crucial to actually generalize the concepts that we have learned as part of just neural network training in general, and that generalizability is what you use in order to say that I can actually deploy this in the real world because I have actually learned something at the end of the day. So interpretability, a more formal definition of it, is just the degree to which we can understand the cause of a decision and then use that to predict a model's prediction. Inception in a sense, where if I have a type of a network and I can say, hey, this part of the neural network is affecting the final output in a particular way, I can claim that I have some degree of interpretability of this model, because I am able to understand some aspect of its inner working and use that to predict what the final prediction will be. For linear regression, this is something that's fairly straightforward, right? Or even simpler, a shallow decision tree. I have an input, right? And I want to say, do you get an A or a B in your class, or do you pass or you fail? I have my grade, which is an X, and a threshold, which is basically, do I have, is X greater than something, 80 for example, right? And if you get more than 80%, you pass. If you get less than 80%, you fail. It's as simple as that. So you can claim that you have interpretability over this model, but this is not very valuable because this is so tiny. You have only one parameter. You literally read up the parameter and you see what's happening under the hood. Now, if you try and scale this to 1 billion parameters, it's not so easy to say, here, this parameter is affecting the model behavior in a particular way, and mechanistic interpretability is doing exactly that. Right? You have 1 billion parameters, you're finding 5 that express a particular concept that we understand at a high level. This is called a feature, and mechinterp is just the process of actually finding that feature. Right? It's easy for shallow learning, like deep learning, which is what, or like a decision tree, which is what we just saw. For deep learning, it becomes much harder because there are a lot of factors that basically affect the final result. So today we're going to interpret these deep neural networks, specifically transformers. I will skip this slide, but the general thesis of this slide is basically Mechanistic interpretability is kind of like reverse engineering a neural network, where you have a binary at the end of a normal compilation process. You can read the assembly, but you can create this sort of obfuscated version of the source code out of that. That's kind of what happens with the training, where you go through the entire process of training, you get parameters on the other end, and you can treat that like a final binary, and now try and figure out what is actually learned under the hood, right? You have your training algorithm, you have your data set, you have the model architecture, and out of that compilation process you get your final model or your final parameters, and you have to try and reverse engineer what it has actually learned or memorized. So that's the general idea, and the technique that actually allows us to do this is called sparse autoencoders. So before we jump into that, let's talk about just the transformer architecture in general. How many people are familiar with the attention architecture at a high level? Like, do you know what we are trying to achieve with attention? Raise of hands. Yes? Okay. Some people. Okay, that is important for this part. Okay, so general idea behind a language model. Are we familiar with like the auto-regressive sampling of language model? Yes, no, raise of hands. Yes? Okay, let's talk about it, I guess. We have a series of words, right? The cat sat on the, and you want to predict what the next word will be. And you basically recursively do this process where you may say the cat sat on the table, and then you want to say, okay, what happens next? You predict the next token. That token could be a word or it could be a part of a word, but for the process of understanding, or just for sake of understanding, you can consider it just a word, right? The cat sat on the table and then jumped back on the floor or pushed over the vase. These are two possible continuations that you can get, right? And the idea behind a transformer is basically just that. You use it to predict the next token, then you add that token that it gets as an output. So if table is the output of this entire feed-forward process, and we'll get into what the feed-forward process is, you will put the word table at the end of this and say, okay, now predict what the next word is. Then predict the next word, and keep doing this over and over and over until you predict, or until the model predicts an end of sentence token or end of output token, at which point it's like its signal to you to tell you to stop generating, and that's like your final answer. The process of the transformer, the process of inference with the transformer that makes it so good is the self-attention mechanism, which is basically a way of saying, of adding context to a given sentence. Now, where did I keep my pen? Wait, what? It was hidden. Okay, very simple example, right? I had a picnic at the river bank, and I went to deposit $5 whole at the bank. Okay, now in both of these sentences, the word bank means two very different things, right? And the high level is that the process of attention allows us to differentiate between these two meanings. In the standard process, right, you start by converting these tokens into their embeddings, their standard word embeddings, and each of these words has a particular meaning, and this meaning is represented as this numeric vector, and we modify or update this representation to give it context from the entire rest of the sentence. So, I had a picnic at the river bank refers to the side of a river, and I went to deposit $5 at the bank refers to the financial institution, and that distinction is what the self-attention mechanism basically allows us to achieve. The next thing, or the general idea or the structure behind the transformer, is that it is followed up after self-attention with this MLP layer. And this MLP layer is basically the core concept that we are going to analyze today. So you have gotten this updated representation of the sentence. So now you understand what the word bank in your input actually means. And now you have to actually do the task, right? You understood that bank means the financial institution bank, but you have to also predict the next word. That's the objective of the language model. So adding that objective, or that actual objective of predicting the next token, is achieved by the MLP in large part, because the MLP has the majority of the parameters within the model. So I think 2/3 of the model is just the MLP parameters, and only 1/3 of it is self-attention. So a lot of things like, you know, the facts that are memorized by the model are embedded within the parameters of this MLP layer. So we go from the tokenizer, which converts the tokens, or converts words into tokens. Then these tokens are then embedded into their sentence, into their word representation with positional embedding, which just gives it information to understand what part of the sequence a particular token is in. So it basically just tells the token SAT that you are in the center of this sentence. Then from there you go to this transformer block, which is the heart of the transformer architecture, right? It contains self-attention followed by MLP, and then you do the transformer block a bunch of times until you get to the very end, where you perform the unembedding, where you're basically converting from the word embeddings of the sentence to the token space again, and then that gives you your final logic sequence, which you use to basically predict what the next token should be like. Yes?
Do you know why they use layer norm instead of batch norm?
I don't know. Most of this is empirical. I'm not going to go into too much of the details for that. Yeah.
That's something I never figured out why.
Well, part of the reason for using layer norm over batch norm generally is that batch normalization is a little bit more unstable. I have my own vendetta with batch norm. I won't probably get into that now, but let's probably not get into that. I don't have a very satisfying principled answer. I think it's just empirically seen to perform better, so we stick with that. The next thing that we need to talk about, I guess one principal answer for that is your batch norm for... No, I don't have a good answer. Never mind, sorry. Okay, awesome. The key idea, again, within the transformer block is to look at the multi-headed attention. So you have H0, H1, and those triple dots. That goes to as many attention heads as you have. That just means attend to multiple different sets of things at the same time, so that you can focus on multiple things. And then the MLP, which is the main thing that we're going to be looking at today. So if nothing else, the thing that you want to keep in mind is that the majority of an LLM, or like a decoder only LLM architecture, is a bunch of transformer blocks, and the transformer blocks first consist of attention to restructure or contextualize the input, and MLP to actually do the task. Okay, and this generally is connected by a residual layer, and usually this is called a skip connection, right? Where I have a layer over here, a layer over here, a layer over here, and the standard forward pass looks a bit like this, and the skip connection basically says take the input from here and add it to here directly. The contextualization that we want to do is to treat the residual stream as this backbone of the actual neural network, and think about the layers as reading from and then writing to this residual stream, where it reads from the residual space, makes some change, and then writes back into it. And this is very relevant because if you create this, if you see like the last two layers, right, you have the unembedding matrix and then you get to final logic space. If you were to create an unembedding matrix for each of the outputs, so for each of the outputs of the transformer block, you will see that the differentiation of the tokens increases every single time. So for example, if this is my logic space, I have 1, 1, 2, and 3 as output when I consider the first transformer block output, and then Y2 becomes a little bit further apart, where this peak becomes a little bit more obvious, because you can see the difference increases increases with respect to each of the other logits. And the idea is basically the task is to separate the main token, the target word, the correct answer from all of the rest of the words, right? You have to kind of pick out what the correct word is. And picking out the correct word becomes much easier as it reads through each of these processes. So I guess maybe more reasonably, you won't be able to achieve the correct answer every single time with the with like an unembedding matrix associated with the first transform block. But if you look at the last 5, they do a pretty good job, right? It's still there is some loss of performance, but it's not inherently terrible, and that is in part because of this kind of structure that we have with the skip connections being the backbone of the network, where it's already really achieved this by some of the middle layers, and then it is just trying to extend that difference further and further as you make a deeper network. So in some cases, when you have more complicated set of logic that you want the network to achieve, what you see is a lot of the inferences that we are going to make and observe is that the first few layers of the transformer architecture recognize some things that are quite low level. So it will identify things like nouns, verbs, and other parts of sentence structure. And the last couple of layers will be identifying more high-level concepts like anger, jealousy, or specific concepts like talking about or words that are relevant to the convolutional network, or just any high-level concept in general, right? So this is something that we can observe empirically, and there is also this the idea of creating the or associating the unembed matrix with each of the transformer blocks to show that linear separation actually increases as we increase the depth of the network. Awesome. So now, given this framework that we've discussed, what stops us from directly just reading the MLP activations and trying to go from there, trying to figure out what it's actually looking for? The main problems, I guess, are polysemanticity and superposition. These are two ideas that basically, or two concepts that are induced as part of the training process, and this enables the model to get very, very good performance at the cost of poor interpretability. So you can't have your cake and eat it too, basically. The idea behind polysemanticity is a particular neuron firing at multiple different concepts. So an example over here was from image circuits, and this is very poorly zoomed in, so I apologize for that. But the idea is that you have this feature of a car, right? And this feature is a high-level word. I use it rather ambiguously, but that is also defined in mechanistic literature rather ambiguously. It can be a set of neurons, a set of activations, or realistically anything in between. But the idea is that it should just represent some high-level concept, and if it does that, you can call it a feature. So the car feature in this case is represented by multiple neurons at the same time, and in addition, the neuron that fires for, I guess, the combination of everything that constitutes a car also fires for things that are relatively unrelated. As an example, for something like an airplane as well, right? So this activation that we are trying to identify within this MLP layer fires for multiple concepts at the same time. So we can't really tell that it has detected a car or a building if we know that a particular activation has fired. And when I say fired, it just means it has a high value, right? So now that is a problem. It fires for things that seem very unrelated, and that doesn't make sense at all, especially if you want to formulate some sort of answer for why these models work so well without just saying that these are stochastic patterns, right? So the other problem that comes into play is that the process of learning compresses larger models into smaller footprints using more denser parameters. And this has been induced by distillation a lot as well, where we simulate the performance of a much more powerful model by basically forcing or encouraging superposition, in a sense where you have a larger theoretical network, and this theoretical network can be monosemantic in nature, wherein it fires for one specific concept only, And this makes it easier for us to understand what it's looking for. However, a consequence of that is that it basically needs more parameters, right? And that is something that it figures out. Just one second, let me just finish this. Where it figures out that by compressing features that are mostly unrelated, it is able to simulate a larger model under the hood, and that gives us better performance, which is a great question.
What is monosemantic and Asian variant?
Monosemantic and?
Asian variant. You mentioned it. When you were saying it, talking about the position.
So polysemantic, I don't know what the second word is.
Maybe I misheard it.
Okay.
What is monosemantic?
Monosemantic and polysemantic, right? So first, polysemanticity is a feature firing for multiple concepts. So I have
just one.
Exactly, yes.
Okay.
I have a car and I have an airplane, and it fires for both of them. So if I have a car in the input, or if there is a car involved in part processing this input, or there is an airplane, in both of those cases it will give a high value, that particular activation, and that makes it difficult for us to identify, is it looking at, or is this value high because of car, or is this value high because of airplane? Question?
So this is my first term hearing of both these terms, and intuitively they both seem to be the same thing.
As in like polysemanticity and superposition?
A denser parameter and a neuron with multiple meanings or multiple concepts. Doesn't it go hand in hand?
It does go hand in hand, yes, but they are different. The difference is admittedly minor, though. It took me a second to figure out myself. So, idea behind polysemanticity is that a particular concept is firing for multiple neurons, and superposition is a virtual network that is sparser in nature, right? So, let's say I have a particular set of activations, right? And this is for some hidden layer L. Is it visible? This is not good. Okay, yeah. So I have values 0, 0, 1, 0, 1. Okay. Now this is very sparse, right? So the idea behind superposition is that I can represent something that is very sparse with something that is smaller and much more denser, right? And polysemanticity is this individual neuron, like this individual element within this vector firing for two different things. So it kind of goes hand in hand, where polysemanticity is induced by superposition because you are compressing an inherently larger model into something that is much smaller, and that kind of encourages more dense representations, which encourages polysemanticity. But the behaviors that are described are technically different, right? But is it a little bit more clear now? We have a sparse network that is initially dense. This could be polysemantic as well as sparse, right? And this is not necessarily a good thing. But encouraging superposition kind of induces polysemanticity, because if I have to represent 5 things using only 2 things, there is bound to be some form of overlap, right?
They complement each other.
They complement each other, exactly, yeah. So one way to kind of describe that is, if I have like a 2D map over here, and I want to represent a feature in this vector space, one way of doing that is just saying that the x, or like the one direction, right, represents one type of a feature, and the other direction represents the other feature, right? So if I have one feature being the existence of car, or like the speed of car in x direction. No, that's a bad example. Let's say one example is a bank being a river bank, and the other example is a bank being the financial institution bank, right? I'll represent this as 1 and 0 when we have one type of bank but not the other. And now the interesting thing to note, right, is that these concepts are technically different, right? It is unlikely to have both a river bank and a financial bank mentioned in the same sentence. You can have a bank by a bank, which is a river bank next to a financial institution bank, but in like sentence structure generally, this is rare, right? And during training, this idea is observed by the network in some sense as well, where two things fire relatively independently, right? Where you have 0, 1 or 1, 0, and you say, okay, let me cheat a little, let me represent this entire thing by just a single value, and if it is positive, I'm talking about riverbank. If it is negative, I'm talking about financial institution bank. And now you just got superposition, right? Because you are representing two different things using the same dimension, and now your model is more expressive because it can express two ideas at the same time. But it did so at the cost of overbooking the flight. Basically, you hope that not everyone shows up, but if everyone shows up, your representation is going to look good, right? Okay, so that is the idea. Any questions? Does it make sense? Kind of? Yes? Okay, good. Analytical setup. Here is how we are going to fix this problem, right? We are going to take the previous architecture that setup is about the same as before. It looks more simple because it is simplified. We ignore layer norm and all of that stuff. And now we see this area in bold, right? The apps and features. Now, the idea behind a sparse autoencoder is the process of dictionary learning. Basically, I say that there is a dictionary that converts these overrepresented features into something that fires sparsely for just those individual concepts. And then I go through and read the concepts, and it kind of unravels the process of superposition, where we get this feature space that is much more larger than our original input, and a consequence of that is that it encourages molar semanticity. So instead of going in one direction where distillation encourages polysemanticity or just training in general because it learns to mix features or mix dimensions, here we are basically encouraging the reverse direction by saying convert this observed model into this bigger, sparser model, and then you can differentiate each of the features in a more efficient way. It still requires a lot of manual effort because you still have to go through a lot of it in order to, or like go through a lot of neurons in order to figure out what's actually happening, but it does make it a more efficient than, or it does make it actually possible, which is the positive. Yes?
Just the activations come out of the MLP.
Yes.
And instead of just using them directly in skip connection, you now feed them through the autoencoder.
Oh, this is separate. Like this is, we don't necessarily use this to influence the forward.
It's just like an internal mechanism put on top.
Yes, exactly. So you're basically creating like a hook on the output of this latent feature and storing it and making a data set out of all of the activations over just a bunch of queries, and then you train a neural network to basically decompose those activations from this small space into this bigger space. And then we study the bigger space to basically figure out what it's actually doing. And that's how we reverse superposition, basically. This is a more formal way of showing that exact thing. You have the standard transformer, or like one toy model setup of the transformer that was there from the previous slide. You have one attention block, one MLP block, the size of the MLP, which is the dimension of the, okay, so in the MLP itself, you have like the result.
Oh, we can't see.
I swear this is not usually a problem. But you have this, for example, in 256, and then this goes up to 512, I guess, from our example, and then you go back into the original feature space. This feed forward process is your MLP stage, right? Now we take the outputs from here, right, or whatever this is, these latent vectors, and then decompose them into something that is even bigger. So you have this.
We can't see it again.
Okay, maybe a bit zoom out.
Yeah.
Okay, and now this is in some multiple of 512, so 1024, and then you recompose this back into R512, right? So this entire process is the standard feed forward, and this entire process over here with the encoder and the decoder is the superposition part of, or not superposition, the SAE or sparse autoencoder part. So crucially, this is sparse, which means that the size of this dimension is greater than the size of our input, right? Which means that theoretically, if you want this autoencoder to achieve zero loss, it can literally just create an identity mapping for the first 5 dimensions and then another one into there, and you get perfect accuracy as far as the reconstruction error goes, right? So that's bad because you're not actually achieving anything. You get an error that looks good, but it has to actually fulfill its purpose, which is to decompose these polysemantic activations, which are firing for multiple things, into just one specific thing. And the way that we do that is by adding this L1 sparsity constraint on the hidden layer activation, which is this over here, where we basically give it a penalty for being dense. So we encourage it to be sparse by simply just adding or by simply just computing the L1 norm of the activations and adding that to our final error term. Questions?
What's that L1 norm?
L1 norm, you have, can you see the thing?
Yeah.
Okay. You have a vector. This is just square root of the absolute value of the individual element within the vector. I guess this is x1, x2, dot 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 till xn.
So it's basically just like,
this is just it.
That's like
it.
a sum over like just a distance
Yeah.
over all of you. Right?
So LP norm is like this, where you do x raised to p.
All summed up. And they take the root p.
Exactly, yeah.
Okay.
X and p, and then 1 over p.
What would break if you use
So
L2?
here p is just equal to 1.
What will break if you use L2?
So we, I think, kind of discussed it
Alright, so yeah. I remember.
during your robot, like Cosmos talk, but I mean, I should talk about it. It's a good point. So we have like the L1 and L2, they create spaces where the optima looks incredibly different. So one has an optima that looks like this. So if you compute the distance x1 plus x1 and then x2, maybe not the best notation, but that, and then you have L2 norm where the optima looks like this. So x2 and then x1. So if I have this 1 equal to 1, that is equal to 1 along this range over here, right? And because of that versus this over here, where x2 is equal to 1, and then you can assume that as you increase that value, just becomes a bigger and bigger circle or a bigger and bigger diamond. The idea is that if you want to find the minima, you are much more likely to find a minima where one is activated much greater than the other because of the fact that you have this discontinuity at the edge over here versus the circle which is continuous everywhere. So you are much more likely to find something, a solution that is a convex combination of the two, and that does not induce sparsity at all because you are using this as a regularization term over some real loss value. L1 motivates using just one feature and completely deactivating the other feature because it allows you to reach each of these 4 extrema. And if your target optima or your like the solution of your problem ignoring regularization falls anywhere beyond the so maybe, for example, if I have the target solution star over here, right, and I am optimizing over L1 norm and L2 norm, and I'm going to kind of merge those two solutions, I expect that I'm going to find some point over here that is closest to the L2 norm, right? Versus the L1 norm, which is much likely to be one of these two. So the L1 norm encourages sparsity because the furthest you can basically extend beyond that regularization plane is the extrema of x1 or x2, versus in the L2 case, it is much more general. And the consequence of that is that you get one firing but not the other for L1 norm, but you get multiple firings simultaneously and not necessarily completely for L2 norm. If the optima was over here, yes, in this case you would get sparsity again, but that's 4 points versus the rest of the entire 360 degrees of the circle, right? So you want to be lucky if you want that. So that's kind of the idea. L1 norm encourages sparsity, and by adding this penalty, we basically create these reconstructions that are sparse by default. Cool. We go from polysemantic activations to these monosemantic features, and the sparse over complete autoencoder is trained against the subjective. That is this architecture over here. It is sparse because we are constraining the activations via L1 penalty, and it's over complete because the size of the activation space is greater than that of the input space. So that the formal definition of this task is dictionary learning, where we want to find this particular dictionary that corresponds to a particular type of a monosemantic recomposed feature, and we want this error to be 0. D is trainable. R is the reconstruction, I think. So we can motivate this objective transformation via a linear factorization. We have xj equal to, wait, what? This should be, I think I fixed this. Yeah, wow, that's cool. Wonderful. B sub D, which is this, which is the bias for decomposition, or sorry, not decomposition, bias for the decoder, plus the result of the actual encoding step, which is Fi. Okay, give me 1 second. This is not feel right. I rewrote it over here. This is the actual notation. Okay, let's focus on equations 5 and 6. This is the exact same thing. You have f of x, which is this output over here, and you have the final reconstruction. This is x hat of f of x, and our loss function is basically the reconstruction of the input plus our sparsity penalty on the output of the hidden layer activations. Cool. So this is our setup, and using this setup, there are only a couple more things that you do to it. The training data is proportional to the number of interpretable features that you want. This is something they just identified empirically, but it's not something that really helps us understand it. It is just a trainee detail, because you want to figure out how much you want to expect that decomposition, or how much you want your model to decompose features. Because if you basically create more outputs within this hidden feature vector, then you have actual features or concepts. What's going to end up happening is it will be forced to fire for multiple concepts, or basically have dead neurons, wherein some activations will basically never fire, or the weights basically get stuck at 0, and once they are basically tracked, these weights that get stuck at some value that is 0, and they resample them in order to improve the actual final feature representation. These are implementation notes from the towards monosemanticity paper. In 2025, probably this is not as relevant. We'll be covering a different paper that does not have to do these kind of tricks, except for, I think, the feature resampling. So now we go to the process of actually evaluating interpretability. It's 8:45, and I'm on slide 12 out of 22. This one I will kind of start skipping now. basic idea was they created a rubric to say that these new activations, these decomposed activations that we have found, are more interpretable than just directly looking at the neurons themselves. They made their own rubric, and they had one of the authors of the paper use this rubric to compute an interpretability score for a pair of features and a pair of neurons, and then they found that without a shadow of a doubt, their process works really well. Then in the automated section, what they did was they said, Claude, come here, here's a rubric, here are inputs, figure out which one looks better by assigning a score to each of these neurons and features, but they didn't tell the model that this is a neuron, this is a feature, and they've also found that neurons are generally more interpretable. Neurons are less interpretable than features. So neurons was just the original activations. Features are the decomposed activations that we have found. One example of the features is the Arabic feature, which is effectively invisible when it is viewed through the standard polysemantic model, where they compute the log likelihood of the of feature activation. So the likelihood of a token, given that a token is Arabic, over just the likelihood, over the probability of just seeing a random token, right? And that is, they computed the log of this ratio in order to identify how likely you were to see Arabic in a particular setting. And despite just representing a small percentage of your training data, the Arabic script for this particular feature that they identified makes up 81% of the active tokens, which is tokens that positively activate for the given feature. So whenever any text from Arabic script was used as part of the inference process, when you basically get the activation over here, it would go through this sparse autoencoder. You would identify a couple of neurons, maybe a combination of two neurons that represent the feature of Arabic, and basically they identified that this would activate every time there was Arabic script in the text, but if there is something that is different, it will not activate. While some of these neurons, whatever dense combination of neurons activates from our activation space, that continues to fire basically at random because of the fact that we have this polysemanticity. It doesn't really explicitly take up a lot of space in terms of the number of dimensions that are occupied by the final by the final latent representation. So that's very interesting. They basically extracted this Arabic feature where before it was completely hidden, and they are able to use this in order to steer generation. So, for example, they found these features and they use this to steer the part of the generation process by using the output from the reconstruction to basically reintegrate this into the feed-forward inference process. So, for example, I have this input or this activation vector over here. I will pass it through the sparse autoencoder, and let's assume that I don't use any Arabic script in my input. So these two features over here that represent Arabic should be off, right? It should be 0. Now, what I do is during the reconstruction process, I have some other sparse combination of features, and I force these two features to be active and set a particular value for these features. Then I pass it through this dictionary that I have learned, and I get this new dense representation that theoretically it should be just the reconstruction of this activation space, but since I have ablated the hidden layer in the middle and I am forcing this interpretable feature to be active, I will basically get a dense representation that is as though the same input existed with Arabic text. So if I plug this in, so if I replace a hat over here with a prime, right, during the feed forward process, I will basically get responses in the Arabic script. And similarly, they did this for Han Chinese, base 64, DNA, uppercase, hexadecimal, and Hebrew. And they found that you input like a series of numbers, you would expect the output to be numbers without any intervention. But when you add these interventions, it changes the behavior of the network. And that change in behavior is consistent with the interpretation that we have identified. So if we go to that definition that we had previously, right, the interpretability is defined as the ability to basically identify some internal concept or some internal feature within the model and use that to predict the model's prediction. So by ablating the model, I am able to guess that, hey, it is going to output something in Arabic script, and in fact that's exactly what happens, which is why you make the claim that, hey, I have achieved some degree of interpretability with this approach. Cool. One unique consequence of this is also finite state automaton in terms of just daisy chaining activations, wherein one token leads to another token activating, which leads to another token activating. Usually we talk about circuits as sets of parameters that lead to these particular types of behavior. Again, I think we are a little short on time, so I won't go too deep into this. But the idea is that one thing activating positively leads to something else activating positively because of just patterns that have been learned. And one token in this chain of tokens activating causes a domino chain of all of these other features also activating. So for the case of HTML, as an example, you get the open brackets, some set of words, and then the open brackets induces the closed brackets to also come in or be predicted towards the end of a particular sequence. That sequence length itself could be arbitrary, it changes, but because of because of induction heads which SAEs are able to identify, we can basically spot this daisy chain process question.
Why is it a state automaton, not a state machine?
Oh, I don't know the difference between state and automaton.
I don't know either. I'm just curious because no state machine have you like is finite state automaton probabilistic or no?
I don't know what the difference between FSA and FTM.
Okay. Never mind.
The paper used the word finite state automaton,
okay.
but I don't know what finite state machine is. Sorry. Yeah. Okay. Wonderful. Updated architecture of SAEs. This is a more modern version. We already discussed this before. This is just the previous setup. And we evaluate how well the SAE performs by how much loss increases when activations are substituted with the reconstruction during forward pass. So we spoke about how we can steer SAEs by forcing certain features to be positive. But suppose we don't do this, we evaluate how well the SAE is performing in terms of just reconstruction error by simply swapping the reconstructions for the original activations. And if at the end of the day the perplexity does not change significantly, you claim that the reconstructions are solid and they're good. This paper observed that the L1 norm motivates shrinkage where it motivates under activation of a particular reconstructed feature because it is easier to toggle between off and on when a feature is only slightly activated during the training process. So it could be that a particular feature is incredibly relevant for a particular concept, but the training process creates this sort of min-max setup where more sparsity makes reconstruction worse, and that basically leaves it at a balance where it's not really the optimal solution. And they fix this by creating a gating path within this sparse autoencoder. So instead of saying that just ReLU is good enough for determining whether a particular feature is on or off, and having that on-off be moderated by ReLU, creating the fact motivating features to be underactivated, you simply create a gating path that is basically just a 1-0 vector, which is element-wise multiplied with a magnitude path, which is just the actual power of a particular concept in the inference process. And as a consequence, they find that they do get more performance, even though this comes with the use of more parameters. So there is always a trade-off. They did some analysis to show that this is a Pareto improvement, so it is better than just scaling up the standard sparse autoencoder. Yes.
I'm just a little bit confused. You have two paths, right? The
Yeah.
first one is your standard one where you just have reloop, right? So that goes through the SAE, right? Do both of these go through the SAE, or?
This is the SAE.
Oh, okay.
This is the SAE. So instead of the SAE architecture just being one decoder and then converting it back into the standard activation space, you use this gating path to create the encoded representation, which is just before the decoder. Right? That is your sparse representation, and double deck decoder converts that back into the original.
So then the gating path, it just adds some bias on top of your original feature representation, and then it's just 0-1 activated. And I'm still a bit confused about the gating path, but that's all.
Yeah. It is exactly what you described. Basically, it's a bias that you apply to the actual encoder itself, because it allows the main problem that we had with the previous setup, right, was that the features are underactivated because.
What does that term mean? What does underactivated mean?
Let's say theoretically, I want this concept can be like the concept of Arabic. I'm using this example. I'll just run with it. Is very strongly represented by these two features over here, right? The training process in general is just W encoder and then the ReLU on top of it, right? So in order to deactivate or make something sparse, the objective or the gradient of this encoding stage has to basically push that activation below 0, right? And it is easy to set basically set it within one gradient update by just having the activations be really low. Because if the activation is very high, you are in a sense committing to that thing always being on.
Okay.
And it is going to take a lot of steps for you to deactivate that sparse activation. And the consequence of that is that it stays close to 0, so that change can be made very quickly. And
so like the gating path allows you to make that change like very fast.
Yeah,
Okay.
because the gating path basically determines on or off, and the magnitude path can determine the actual magnitude. So if we want to determine that this connection needs to turn off for whatever reason, you simply make that bias the bias for that value really small, and that gives you the ability to make a big jump, and you're sorted.
Cool, makes sense. Thank you.
They use also a more complex loss function. Again, not getting into it because I want to run into the code, and I have 3 whole minutes for that. So that's suboptimal. Okay. I'm trying to convert to my laptop because I have Neuron PDF over here. It's not showing up. Come on. I really hope I don't have to log in to do this.
It could be that you're running minus.
Don't go there. Do not go there. Okay. Please don't make me log in. Okay, wonderful. So here's an example of just steering a model using using an autoencoder. We have a Gemma 2B 9 billion parameter model that we want to steer, and we have a couple of examples that we can use. So let's go for which one? Negativity mode. Sure.
Yeah.
I did a similar experiment to this with some manual parameters earlier today. It's very fun. One more time? Sorry?
You asked you to incur just to pass TS587.
Okay.
Or make some choice words about it.
No, let me. No, this is being recorded, brother. Okay. Boost negativity, right? So tell me a story.
Like a bad day.
Okay, old woman, Elara sat on her porch swing. It's a nice story. An old woman sat on her porch swing with the chains groaning like a cough. The wind whipped through the willow tree in a yard. Yeah. So basically, the idea is that with this setup, you have the model that is giving you a response that is much more aggressive. Now, I will say that these are incredibly cherry-picked in the sense that it looks like this works really well, right? Oh, this is so impressive. But in practice, if you were to actually go in and try and figure it out, you require a big combination of things in order to really get this to work right. And we can try this a little bit interactively. It will take maybe 5 minutes, but I won't take longer than that. Does anyone have ideas for what we want to steer the SAE towards? So we tried negativity mode. Let us try.
Can do people like Elon? They could talk like Elon.
Sure. How does Elon talk?
That's a good question. Will it be able to infer how he can turn out?
Well, I mean, so I guess procedurally, how we want to figure this out, right? I will go to select the actual model that we are trying to run inference over. There are two residual streams that we can pick up from. These are just two SAEs. And I will pick the last couple of layers. Actually, wait, I think, yeah, that's okay. I guess we can just use this. Let's just type, I am Elon.
Proud.
I am Elon Musk. I don't want to be incredibly negative here. So maybe we can try someone who's nice. Okay. No, let's just try something else. Let's try arrogance, okay? I am an incredibly intelligent, self-obsessed.
Selfish. What else?
Condescending.
There you go. Narrow
Person.
Please.
What? Me. So we're actually being Shrek, I guess, in this case. So now the idea is to actually just introduce this a little bit more conceptually rather than show us something that gives us a working example. But the idea is that I run this inference, and now I can self-select a couple of tokens that I want to see that activates really, that we want to see features that activate really strongly for this particular subset of tokens. So let's go intelligent, self-obsessed, all of this. And then, okay, sure. Now, when this search completes, it will give us a series of features that have activated very positively for these subset of words. And the explanations that are associated with these words are presented over here. So we have words and phrases associated with self-centeredness and altruism, self-related concepts or attributes, and so on and so forth. So we can identify, I guess, one feature from here, and go to steering. We have Gemma 9B IT. I'm going to add a feature from res 131K feature 26286, right? So 262.8 and 6, and this feature basically is, oh wait, did I get it wrong? 9B IT. Oh, this is 6. Okay, what am I doing here? 20. Oh, layer 20, not 31. Okay, and this 262.86. Alright, when I hit go over here, we get terms related to self-centeredness and selfish behavior. And now I'll say good morning, and probably it will say something that is very similar, right? Like this does not scream self-centered at all. And if I kind of push this to an extreme, right, I am going to observe it using these terms rather than actually being selfish or self-centered. So if I try good morning, and I'm going to look very silly if this does not end up working, but yeah, we can identify that within the outputs, firstly, obviously this doesn't make any sense. This is no longer English, right? But also the words that are output over here, greedy, selfish, selfishness, are words that are present within the stop activation space. So the main idea that I'm trying to motivate here is the concept of steering SAEs, right, is not inherently telling it to generate a particular thing. It is basically influencing the context that within which the input is received. So it is as though I said good morning in a very selfish way to this model, and the output of that is this sort of gibberish, because it is something that is basically out of distribution, right? I have sent this model into some OOD space where it forgets all of its English and only focuses on this overactivated feature. So we can play around with this and find a decent middle ground where something actually happens and it still is consistently English, but that is not very straightforward to do. And also in most of the cases, if you respond in a mean way to the model, these models are trained with RLHF to explicitly ignore that type of behavior. And a consequence of that is that in a lot of cases, even though you forcefully overactivate something, you are not going to actually get an explicit change of behavior. So it is a very good proxy if you get it to work well. But the two important things to keep in mind are you are influencing the context within which a model is outputting a response, not the not a directive towards the type of behavior you want to see, which is why prompting is still used very, very prominently. And the other thing is the daisy chain part from here, where you have logics that overactivate the other, or like that forcefully activate the other. And this happens in some sense for the actual model itself, right, within the single feed-forward inference process. So if you attempt to activate features from layers that are very close towards the end, so this has 32 layers, I think, this is about 20, this is somewhere in the middle. If you use, I think, Llama 3.3 has SAEs trained for every single layer, and if you try and modify some of the earlier layers, you will reach an OOD space very quickly, because one layer relies on the output of the other. So in practice, if you are actually trying this, try for some of the last couple of layers and you will probably see your best result in that case. So yeah, that's the kind of empirical aspect of your playing around with SAEs. They are a very, very cool concept. So if you found this interesting, please try looking into this a bit further. Resources for that are over here. Arena.education is incredible place to actually learn about and play around with sparse autoencoders and mechanistic interpretability in general. So awesome. That is all I had for today. Thank you very much for coming. I hope you enjoyed.